Hello all. In my previous lecture, I discussed what is the energy band diagram and how it forms and classification of the materials based on energy band diagram. And one of the classification I discussed, that is insulator. Now in this class, I will start with the semiconductor. What is a semiconductor? Semiconductor means the material whose energy gap is approximately very small, that is 2 electron volt, right? Such a material is called as semiconductor material at T equal to 0 degrees Kelvin. Temperature is 0 degrees Kelvin. Thermal energy supplied to the valence electron is 0. That means no thermal energy is supplied to the valence electrons. Then no valence electrons are moving from valency band to conduction band. If no electrons are moving from valency band to conduction band means the conduction band is empty. If conduction band is empty means what about the semiconductor? The semiconductor acts as a insulator at T equal to 0 degrees Kelvin. Right? Next, what is the average thermal energy supplied to the semiconductor? KT, where K is the Boltzmann constant in electron volt per Kelvin and T is the temperature in Kelvin. And what is the K value here? Actually, the K is nothing but 8.6 into 10 power minus 5 electron volt per Kelvin. And what about the K bar here? K bar is nothing but 1.38 into 10 to the power of minus 23 joules per Kelvin. This is the difference between K and K bar. And one more point actually, the average thermal energy supplied to the valence electrons at room temperature. Room temperature means 300 degrees Kelvin actually. So what is this value actually? This value is nothing but simply 0.026 electron volt. This is the value at room temperature. Okay, write down up to so far. Semiconductor, the material whose energy gap is approximately very small, that is approximately 2 electron volt, in bracket approximately 2 electron volt. Such a material is called as semiconductor. At T equal to 0 degrees Kelvin, thermal energy supplied to the valence electrons is 0. Due to which no electron is moving from valency band to conduction band. And conduction band is empty. Such a material is called as insulator. Means semiconductor acts as a insulator at 0 degrees Kelvin. Next point. The average thermal energy supplied to the valence electrons is given by KT. Underline KT. Where K is the Boltzmann constant in electron volt per Kelvin and T is the temperature in Kelvin. Temperature in Kelvin. Yeah. Write down the values, K and K bar values. Next point. The average thermal energy supplied to the valence electrons at room temperature is given by 0.026 electron volt. 0.026 electron volt. Underline 0.026 electron volt. Yeah. Next, see, if the temperature is increases, what happen? Thermal energy is supplied to the valence electrons. That means all valence electrons are acquiring the thermal energy. After acquiring sufficient thermal energy, the valence electrons are moving from valency band to conduction band. Sufficient thermal energy means which is greater than the energy gap. Okay, and it can move into conduction band. Then the vacancies are created in the valency band. These vacancies are called as holes. What it called? Holes. See, if one electron is energized, for example, if one electron is energized, okay, and it can produce what actually? And it can produce a electron hole pair. Energized means if you supply the thermal energy to one electron, okay, and it can produce free electron hole pair. This process of producing of free electron hole pair due to thermal energy is called as what actually? Thermal excitation. What it called? Thermal excitation. Right? Next, see, when an external electric field is applied, supplied, what happens? The electrons can move in conduction band. Which electrons can move in conduction band actually? Free electrons. Okay, and it can produce a current. That current is nothing but what actually? Free electron current, and it is denoted by IN. Similarly, the electron present in the valency band. Electron present in the valency band means which electrons actually? Bounded electrons. And it can move and produce a current. That current is called as what actually? Hole current. That is denoted with I. Right? That means in case of semiconductor, what will be the total current actually? The total current is nothing but I total equal to IN plus IP. Right. Write down. Please note down the points. When the temperature is increases, thermal energy is supplied to the valence electrons. Thermal energy is supplied to the valence electrons. After acquiring sufficient thermal energy, the valence electrons can move from valency band to conduction band. Then the vacancies are created in the valency band. These vacancies are called as holes. Next point. If one electron is energized, then it can produce free electron hole pair. This process of producing of free electron hole pair due to thermal energy is called as Thermal excitation. Thermal excitation. Yeah. Underline thermal excitation. Next point. When an external electric field is applied, then electrons can move in conduction band, in bracket free electrons, and produce a free electron current IN. Please underline free electron current. Similarly, due to applied external electric field, electrons move in valency band, in bracket bounded electrons, and produce a whole current, in bracket IP. Hence, the total current is given by, write down, I total equal to IN plus IP. Right. Also copy this energy band diagram. For semiconductor. Right. Completed? Next, tell me what are the examples for the semiconductor actually. The example for the semiconductors are silicon, germanium, graphite. Okay. These are called as elemental semiconductors. And one more example actually, that is gallium arsenide, gallium phosphide, indium phosphide, gallium arsenide and phosphide. These are called as compound semiconductors. Actually, we have two types of semiconductors: elemental semiconductors and compound semiconductors. Copy the examples. Yeah. Next, what is a compound semiconductor? Compound semiconductor is nothing but a mixing of third group and fifth group elements is called as compound semiconductors. Actually, what are the third group elements actually here? The third group elements are nothing but boron, aluminium, gallium, indium, thallium. And what are the fifth group elements actually? The fifth group elements are nothing but nitrogen, phosphorus, arsenic, antimony. These are the fifth group elements. Now tell me here, what is the compound semiconductor? Mixing of third and fifth group elements. Nothing but here, gallium phosphide, gallium arsenide, gallium arsenide and phosphide, indium phosphide. These are the few combinations actually. Okay, and elemental semiconductors are nothing but those are related to fourth group actually. See here, what is the fourth group elements? Carbon, silicon, germanium, and tin, etc. Nothing but tin and lead. Right? You know, the carbon can act as both a semiconductor as well as a insulator. Okay, the example for the semiconductor is graphite, and the example for the insulator is diamond. Right? That's why even though the carbon acts as a semiconductor, but we cannot prefer the semiconductor because carbon has unstable behavior. Because of this unstable behavior, even though it can act as a semiconductor, we cannot prefer it as a semiconductor. We cannot prefer it as a semiconductor means we are not using for manufacturing of an electronic devices. Okay, only we are using two materials, that is silicon and germanium. Okay. These are called as elemental semiconductors. Right. Copy this one also. Yeah. Next. Write in a note. Carbon acts as semiconductor. Carbon acts as semiconductor, but it cannot prefer the semiconductor. But it cannot prefer the semiconductor because of unstable behavior. Because of unstable behavior. Unstable behavior. Right. Yeah. Next. Coming to classification of the semiconductor. You know, the semiconductors can be classified into two types. Based on what actually? Based on EK plot. EK plot is nothing but energy versus momentum plot. Right? So based on EK plot actually, my semiconductors can be classified into two types, that is direct band gap semiconductor, direct band gap semiconductor, and the next one is indirect band gap semiconductor. Okay. Now you have a doubt. See, what is EK plot? What is energy versus momentum plot actually? How energy and momentum will be related? Based on that, how the semiconductors can be classified into two types. Now see all of you. See, when an external electric field is applied to a semiconductor, what you can observe actually? The electrons are moving in both conduction band as well as valency band. Free electrons are moving in conduction and the bound electrons are moving in valency. That means electrons are moving in conduction and valency, right? Conduction band and valency. Okay, what type of energy it possesses actually? Kinetic energy, because a moving object always having kinetic energy, right? That is K equal to half mv square, right? See, we are applying some external electric field, the electron is moving, right? That means having some momentum. Momentum is nothing but, it is denoted with K, nothing but mass into velocity. Now tell me, what is relation between momentum and energy actually? K equal to half into kV, right? Now this is the relation between energy and momentum. Based on this relation, my semiconductors can be classified into two types, that is direct band gap semiconductors and indirect band gap semiconductors. Right? Now first we talk about direct band gap semiconductor. What is direct band gap semiconductor actually? Direct band gap semiconductor is nothing but the semiconductor in which the conduction band is minimum and the valency band is maximum at same momentum. Actually here this is the plot of energy versus momentum plot actually here. We can define the direct band gap semiconductor based on energy versus momentum. What I am saying here, the semiconductor in which the conduction band is minimum and valency band is maximum at the same momentum. Such a semiconductors are called as direct band gap semiconductor. Right? Now when the electron is coming from conduction band to valency band, conduction band to valency band at the same momentum is called as what actually is called as a direct recombination. Is called as direct recombination. Yeah, recombination. What is recombination? You know, recombination is nothing but if electron is coming from conduction to valency, that is called as recombination. For example, if electron is moving from valency to conduction, that is called as generation. See what I'm saying here? Generation. What is generation actually? Generation is nothing but if electron is moving from valency to conduction is called as a generation. Okay. Recombination is nothing but if electron is moving from conduction to valency is called as recombination. Now here it is at the same momentum now, that's why it is named as direct recombination actually. Right? Next, here during this direct recombination, my electron will release the energy in the form of what actually? In the form of light. Right? You know this light energy is almost equal to what actually? Energy gap. Okay. Now see all of here, light energy is denoted with actually h nu, which is equal to the energy gap. Now what is the nu in terms of lambda actually? C by lambda, which is equal to Ag. Now what is lambda here? Lambda is nothing but h is C by Ag. What is h? H is nothing but the Planck's constant, that is 6.625 into minus 34 joules. Okay, C is nothing but velocity of light, that is 3 into 10 power 8 by Eg. But actually energy gap always expressed in terms of electron volt, right? That's why here I can divide with 1.6 into 10 power minus 19. Now what is this value lambda here? Lambda is nothing but 1.24 micrometer by energy gap in terms of what actually? Electron volt. This is the relation between lambda and energy gap. Right? Now here, so from this relation what we can understand actually here, how this lambda and energy will be related inversely. Means as energy gap is increases, then what is the lambda here? Decreases. And very important relation actually. Right. This is about direct band gap semiconductor. Right? Write down your notes. Semiconductors can be classified into two types. Semiconductors classified into two types based on EK plot, in bracket energy versus momentum. Energy versus momentum. Yeah, bracket close. Now write down the relations, these three equations, how they related actually, energy and momentum. Right. Next one. Write down the first one, direct band gap semiconductor. The first one, direct band gap semiconductor, the first classification. direct band gap semiconductor. Write on the definition. The semiconductor in which conduction band is minimum and valency band is maximum at the same momentum is called as direct band gap semiconductor. Yeah. Next point. When the electron is coming from conduction band to valency band, at the same momentum is called as direct recombination. Please underline recombination. During direct recombination, electron release the energy in the form of light. Please underline in the form of light. Yeah. Next point. This light energy is almost equal to energy gap. Yeah. Energy gap. Now, write down this relation. Next, up to so far here. After this, you can write down this one. After completion of that one, write down the EK plot for direct band gap semiconductor. Draw this plot. Yeah. Yeah. Next classification. Heading indirect band gap semiconductor. Indirect band gap semiconductor. Yeah. So now, see first, what is the indirect band gap semiconductor? The semiconductor in which the conduction band is minimum and valency band is maximum at different momentums. Here in case of direct, same momentum, but here it is different momentums. Such a semiconductor is called as what actually? Indirect band gap semiconductor. Okay. See, when an electron is coming from conduction band to valency band at different momentums is called as what actually? Indirect recombination. Indirect recombination. You know, during this indirect recombination actually, my electron is released energy in the form of what actually? Heat. Okay? Heat energy. This heat energy is almost equal to what actually? Energy gap. Okay? Right on? The semiconductor in which, write in your notes, the semiconductor in which the conduction band is minimum, and valency band is maximum, at different momentums, Such a semiconductor is called as indirect band gap semiconductor. Yeah. Next point. When the electron is coming from conduction band to valency band, at different momentums. Such a semiconductor, it is called as indirect recombination. Yeah, please underline indirect recombination. During indirect recombination, electron release the energy in the form of heat. Yeah, underline in the form of heat. Now copy the EK plot for indirect band gap semiconductor. Copy the indirect band gap EK plot. Yeah. Next heading, observation. Yeah. What you observed in direct band gap semiconductor and indirect band gap semiconductor actually. In case of direct band gap semiconductor, okay, it emits light. That's why these direct band gap semiconductors are used to manufacturing of light emitting diodes. Like LED, laser. Okay. Example, gallium arsenide and indium phosphide. Actually, these two semiconductors are used to manufacturing of invisible LEDs. Invisible, or we can also say infrared LEDs. Okay. Next, gallium arsenide and phosphide. These are used actually manufacturing of visible LEDs. Right. This is about direct band gap semiconductor. Coming to indirect band gap semiconductor actually. Okay, in case of indirect band gap semiconductor, what is the released energy actually? Heat. That's why it is used to manufacturing of electronic devices like diode, transistor, SCR, etc. Okay. Now, what are the examples for indirect band gap semiconductor actually? Simply silicon and germanium. Silicon and germanium. Now tell me, what is the conclusion actually here? The conclusion is, here the direct band gap semiconductors are nothing but compound semiconductors, and indirect band gap semiconductors are nothing but elemental semiconductors. Right? Write down the observation and conclusion. The first point, the direct band gap semiconductors are used. The direct band gap semiconductors are used to manufacturing of light emitting diodes like LED, laser. Example, write down examples. Yeah. Second point, indirect band gap semiconductors are used. Indirect band gap semiconductors are used to manufacturing of electronic devices like diode, transistor, SCR, etc. Diode, transistor, SCR, etc. Right? Yeah. Write down the examples: silicon and germanium. Yeah. Next, conclusion. The first point: direct band gap semiconductors are compound semiconductors. And the second point, indirect band gap semiconductors are elemental semiconductors. Right? Yeah. This classification is based on EK plot. Next topic, energy gap. See, what is the energy gap of silicon at 0 degrees Kelvin? Actually 1.21 electron volt, and at 300 degrees Kelvin this is 1.1 electron volt. For germanium this is 0.78 electron volt, and at 300 degrees Kelvin actually 0.72 electron volt. Very important competitive questions. Right? Here, how to calculate these energy gap values at different temperatures? Right? Now see, we have standard equations actually. See, at any temperature for silicon, what is the energy gap actually? Energy gap is nothing but 1.21 minus 3.6 into 10 power minus 4 into T. Right? See, for germanium actually energy gap equal to 0.78 minus 2.23 into 10 power minus 4 into T. Okay. Based on these equations actually we can calculate the energy gap at different temperatures. That means what we can understand, actually the energy gap depends on what? Actually it depends on the temperature. Right? Here, as temperature is increases, what about the energy gap here? Actually energy gap is decreased. See, what happens if temperature is decreases inside a semiconductor material? Actually the lattice spacing is decreases, so energy gap is decreased. Means interaction between the atoms is increases actually. Okay, so energy gap is decreased. Very important relation, right? Copy. Yeah. All of you see the table actually once. Here, so which material having less energy gap actually here? Germanium. See, germanium has less energy gap and also it offers high conductivity than silicon. But silicon is preferred in fabrication than germanium. Why? Yeah. Here, why we prefer silicon than germanium even though it offers high conductivity actually? Okay, because the first one is silicon has less leakage current. Silicon has less leakage current since it has high energy gap. Okay, see for silicon material actually what will be the energy gap actually here? 1.21, right? Okay, then what about the reverse saturation current actually here? In order of nanoampere. In case of germanium, what is the reverse saturation current actually? N microampere. Now, so which one has less leakage current actually? Silicon. That's why we prefer silicon. This is the primary reason. And the second point is actually silicon has better physical characteristics. Okay, due to which it can operate at a wide range of temperature, that is minus 55 degrees centigrade to 125 degrees centigrade. That means it is thermally stable, right? And one more point actually, silicon is available in the form of what actually? Silica. So which makes the fabrication process very easy. That's why we prefer the silicon. And the last point but not least, silicon is the second most abundant element on earth. Second most abundant element on earth. So because of these four reasons actually, even though germanium offers high conductivity, we prefer silicon in fabrication. Right? Very important one. Write down. Germanium has less energy gap and high conductivity than silicon. But silicon is preferred in fabrication. Silicon is preferred in fabrication than germanium. Because the first point, silicon has less leakage current. Since it has high energy gap. Right. I don't for silicon I naught in nanoampere. For germanium I naught in microampere. Yeah. Second point, silicon has better physical characteristics so that it can operate at wide range of temperature. That is minus 55 degrees centigrade to 125 degrees centigrade. Yeah. Third point, silicon is available in the form of silica. Which makes the fabrication process is very easy. Yeah. Fourth point, silicon is the second most abundant element on earth. Right? Because of these four reasons, we prefer silicon in fabrication than germanium. Yeah, thank you. I will continue in next lecture.